Hello class. In our previous lecture we talked about and introduced the idea of chemical bonding. And in particular one of the things we talked about is how chemical bonds are what's used in order to satisfy the octet rule for individual atoms. And so one of the things that we talked about is we looked at a sodium atom which has 1 valence electron and a chlorine atom which has 7. And we said that they need to satisfy their octet rule. And in particular, the best way for these two atoms to satisfy their octet rule was to transfer 1 electron from one atom to the other. This leaves sodium without any valence electrons, and it becomes sodium 1+. And this takes chlorine, and instead of having 7 valence electrons, it now has an 8th valence electron, and so it's chlorine 1-. And I reminded you how, and when we talked about in the first unit, that whenever a positive charge or a cation meets an anion, they experience a strong attractive force. So this sodium and this chlorine tend to stay stuck together and form the compound sodium chloride. And so last time in particular we talked about how to use the oxidation states of the elements to predict the chemical formulas, and we talked about things like polyatomic ions. Now, something to keep in mind from this lecture that a lot of people, from the previous lecture, that a lot of people missed is the fact that ionic bonding while it's true that it tends to be between a metal and a non-metal, this is the easy definition, and it is usually true, but it is not always true. And in fact, what is always true is that ionic bonding is between ions of opposite charge. My pen's dying on me. Ions of opposite charge. And this really is the important part of the definition that a lot of people kind of skip over, in particular on homework assignments where you're asked what kind of bond forms between ammonium and sulfate. Probably the most common mistake that I get here is you want to call it covalent because nitrogen's a nonmetal, hydrogen's a nonmetal, sulfur's a nonmetal, oxygen's a nonmetal. It's true that all of these are nonmetals. That's wonderful. However, we also talked about polyatomic ions and how they can substitute metals and nonmetals in ionic bonds. So in other words, what's important is not whether these are metals or nonmetals, but the fact that this is a cation and this is an anion. Therefore, they form ionic bonds. So hopefully that was the clarification that a few people were asking for on that particular topic. And when I reviewed over your homework assignment, that was a question that quite a few people missed. And so if you missed this question, then you need to go back and listen to the video again. I was very explicit about this in the video, that if you have ions of opposite charge, it does not matter if it's metals or nonmetals. It's an ionic bond. And that should make sense. So I'd like to take the rest of the video and spend time talking about our next topic, which is covalent bonding. Now you should have covered a great deal of the material already, but I'm going to take some time to kind of expand on a few points. So in particular, one of the things that you looked at in the videos or in the notes is you looked at the idea of 2 chlorines bonding together. So here I've done what we call the Lewis dot of the elements for chlorine. So you'll notice that I separated the electrons into 4 regions around the chlorine. Now I might ask you, why? Why 4? So it goes back to the valence shell. Reflect back over your definition of valence electrons in particular. Valence electrons are outer s and p. So they're the outer s and p subshells. An s subshell has one s orbital. A p subshell has three p orbitals, which means there are four valence orbitals. So in writing the Lewis dot structure of the element, we take the 7 valence electrons that chlorine has and we position them in the valence orbitals around chlorine. The other thing you should keep in mind is that each individual orbital can only hold 2 electrons. So when I start with chlorine and I know I have 7 valence electrons, I'll start and put 1 in each orbital. So 1, 2, 3, 4. Then, once I've put 1 electron in each orbital, I'll pair them up until I run out of electrons. Okay, and you get the Lewis dot structure of chlorine. And I just did the same thing with another chlorine before. Now, what's nice about these two Lewis dot structures is it becomes a little bit more obvious how we're going to satisfy the octet rule using covalent bonding. So if you reflect back on your notes from the previous lecture, covalent bonding is a sharing of electrons between two atoms. So in particular, what's going to happen is both of these chlorines have mostly paired up electrons, but they each have one unpaired electron. So each of them donates one of the unpaired electrons to the other, and they share those 2 electrons between each other to form a bond. Which we also sometimes call a shared pair. And then we have left over on specific atoms what we call lone pairs. And shared pairs and lone pairs are something we'll be revisiting in future lectures, so don't forget them. So it should be pretty obvious to see that 2 chlorine atoms are going to form a single bond with each other in order to satisfy their octet rule. In other words, now I can cover 1 chlorine and we can look at this chlorine and say, okay, is the octet rule satisfied? Well, 1, 2, 3, 4, 5, 6, 7, 8. So yes, the octet rule is satisfied for that chlorine atom. And the same could be said of the other chlorine. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so by each one of them donating 1 electron and then sharing the result between them, they both satisfy their octet rule without becoming charged like in ionic bonding. In other words, both of these 2 chlorines could still be considered neutral because they each only have 7 electrons that they brought, and then they're sharing electrons with the other chlorine. So we can think of these 2 chlorines as completely uncharged. Consider oxygen. Take a moment and see if you can draw what oxygen must look like. So start with the Lewis dot structure. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you should notice that you have 2 completely paired up lone pairs, and then each oxygen has 1, 2 unpaired electrons. And so those unpaired electrons will be used to make bonds. And we could redraw oxygen. Like so. Okay, so why don't you take a moment and now try nitrogens. And I'm going to pause on the video to give you a second to try this, or to give you a second to pause the video before I go ahead and talk about what nitrogen would look like. Okay, so nitrogen's a group 5 element, so it has 5 valence electrons. 1, 2, 3, 4, 5. Same thing here. 1, 2, 3, 4, 5. So we see one lone pair and 3 unpaired electrons on each nitrogen. So we could expect that the 2 nitrogen atoms would form 3 bonds with each other in order to satisfy their octet rules. And we could redraw dinitrogen like this. Okay, so it's actually pretty neat how easy it is to predict what the formula is going to look like whenever we're dealing with 2 of the same types of atoms. Now in our next lecture, we'll be talking about Lewis diagrams in a lot of detail, and we'll learn that sometimes it's not quite so simple. And so this is a very easy way of doing molecules that are diatomics of the same element, but sometimes we're going to need a little better way of thinking through these types of problems. But for now, this should give you an idea of how 2 atoms can satisfy their octet rule by sharing electrons with each other. Now I'd like to add in a new idea. And in particular, this is something you should have already covered in your notes very thoroughly, but I want to make sure we talk about it some more because I consider it one of the single most important ideas in all of chemistry. And it's called electronegativity. Which sometimes, when you're reading bio textbooks or anything else that references chemistry but is not chemistry, sometimes you'll hear it referred to as electron affinity. And so whenever we include the word affinity, I think it becomes a little more intuitive exactly what electronegativity is. It is essentially how much an atom likes electrons, and in particular vice versa as well, how much electrons like that atom. So if we gave it a very informal definition, I would say it is how strongly an atom attracts and holds onto new electrons. Okay, and I'd like to expand your understanding of this definition just a little bit. So in particular, let's think about the valence orbitals of 2 different atoms. So we know that the valence shell is the outer s and the outer p's. So I'm going to indicate the valence shell by doing a p subshell preceded by an s subshell for some random atom. Okay. Then I want you to consider another atom's valence shell, which is also 3p orbitals and 1 s orbital. So something that you should notice is that this is drawn much lower. This one is drawn much lower than this one is. And so something I want you to think about is as we go higher on the diagram, energy is increasing. In other words, these orbitals are at a much higher energy than these orbitals. So consider the 2 following atoms. And I know I'm filling in this diagram. Don't worry too much about how I'm going about filling this diagram. It's not something I'm going to push as a topic in this class. But just understand that these little half arrows represent an electron. These dashes represent orbitals. Okay? And the higher up the orbital is, the higher the energy of the orbital. So something that you'll notice is that this atom has 6 valence electrons. 1, 2, 3, 4, 5, 6, which means it has room for 2 more. Whereas this atom has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7, and has room for 1 more. So my question to you is, which one would you expect to be more electronegative? In other words, between this spot and this spot, which one would an electron prefer? In particular, I want you to think back on the definition of energy that I gave you in the third and fourth lecture, where we said think of energy a little bit like stress. And so everything wants to be at as low of an energy as possible because everything wants to have as little stress as possible. So which one of these two atoms would an electron prefer? And which one of these two atoms would do a better job of holding on to its new electron? Hopefully you said this was the more electronegative of the two, mostly because it has an opening at a much lower energy than the openings on the other atom. So whenever we say one atom is more electronegative than another, what we're really saying is that the more electronegative atom has some orbital that's available at a lower energy than the atom that it's being compared to. Now, fortunately, we don't have to draw energy diagrams every time we want to compare the electronegativity of two different atoms. Instead, there's actually a periodic trend of electronegativity. I almost ran out of space there. Periodic trend of electronegativity. So I'm going to sketch a small periodic table. All right, so this is a pretty rough sketch of the periodic table. Oh, slide this up. This is a pretty rough sketch of the periodic table. So to give you some perspective, over here to the far right are the noble gases. Or in other words, group 8 of the main groups of the elements. So since it's group 8, how many valence electrons do they have? Hopefully you said 8. So in particular, what that means is they have a filled valence shell. In other words, noble gases tend not to form chemical bonds very often. Under the right conditions they can, but as far as we're concerned in our class, noble gases never form chemical bonds. In other words, would you expect a noble gas to have very high electronegativity? Hopefully not. Since they don't have an open orbital anywhere in the noble gas, because they have a filled valence shell, it tells you that they do not have a low energy available orbital, so they're not very electronegative. And in terms of the trend that we're going to talk about, the noble gases are really the exception. Okay, they never have high electronegativity, and they almost never form chemical bonds. So other than that, some key points to talk about on the periodic table is just to the left of the noble gases, that's fluorine. And down here in this bottom corner is francium. So the periodic trend of electronegativity says that electronegativity increases as we go up and over in the periodic table, meaning that fluorine is the most electronegative element and francium is the least. And so, in other words, it increases as we go up a column. So for any given group, the most electronegative member of that group is the one at the top of the column. And it increases as we go right across the periodic table. So for any given row, the most electronegative member of that row is to the far right of the periodic table, but not including the noble gases. Because we're keeping in mind that the noble gases have very low electronegativity. So let's do a quick exercise to make sure that you have a hold of this idea. So consider the following three lists. So let's say sodium, francium, potassium, and rubidium. Rank these four from most electronegative to least electronegative. All right, so we find sodium on the periodic table, we find francium, we find potassium, and we find rubidium. So we know that since these are all in the same group, that the member that is the highest in the group is the most electronegative. So sodium is most, which is greater than potassium, which is greater than rubidium, which is greater than francium. Okay, we could try another list just to make sure we have the trend down. Let's consider cesium, fluorine, copper, molybdenum, and nitrogen. Right, so this time they're not all in one column, so I have to really take a look at it on the periodic table. I'm going to pause for a few seconds in the video to give you a chance to try to list those from most to least, and then I'll go over the answer in a minute. So if we find them on the periodic table, first we've got cesium, we had fluorine, copper, molybdenum, and nitrogen. So now that we've found the spots on the periodic table that we're talking about, it's pretty easy to see. Electronegativity increases as we go up and over, so fluorine's the most, followed by nitrogen, followed by copper, then molybdenum, and then cesium. Now something that you might notice on the periodic table is there are some things that are a little ambiguous. So in other words, if you consider starting at fluorine and you wanted to compare something like nitrogen with something like bromine, this is a very difficult comparison to make. And I would never expect you to know which one is more electronegative. And in fact, in these situations, I'll give you some information that clarifies which one is more electronegative so that you need to know, as you need to know. In other words, we only know which one's more electronegative because we measured it in an experiment. And so it's hard to tell just from looking at the periodic trend. The only ones I would ever expect you to know are ones that are very obvious, like nitrogen and fluorine. Fluorine is distinctly more electronegative than nitrogen, according to the periodic trend. Okay. But again, I would never ask you to compare oxygen and chlorine. Just for the record, oxygen is slightly more electronegative than chlorine. Oxygen is the second most electronegative element on the periodic table. Now that we've talked about the idea of electronegativity, we can take another look at covalent bonding. So let's consider carbon and chlorine this time. So we can draw in our Lewis dots. Now, carbon and chlorine can't bond together on a one-to-one basis like I'm showing here. But what I really want to do is just think about the one bond that carbon and chlorine can form. So we know carbon's going to give up one electron to the bond, and chlorine will give up one electron to the bond. This will satisfy chlorine's octet, but it'll leave carbon to form bonds with some other atoms in leave carbon to form bonds with some other atoms. But what we're really just concerned about is this bond between carbon and chlorine. So earlier, when we looked at two chlorine atoms, we would expect that these two chlorine atoms would share these two electrons evenly because they're the same atom. And if we think back on electronegativity, we can say that these two chlorines have the same electronegativity because all chlorines are equally electronegative. And since neither one of them is stronger than the other, they hold on to the electrons equally. And therefore each chlorine could be thought of as neutral. But when carbon and chlorine make a bond, if you check your periodic trend of electronegativity, you can expect that chlorine is more electronegative than carbon. So rather than sharing the two electrons evenly like the two chlorines do, our chlorine gets a little bit more say over the electrons. So we could think of the two electrons in the bond as being a little bit more chlorines than carbons. And this should be pretty easy to think about. In particular, you can probably think of some things that you've shared with roommates or spouses or maybe even your kids where, it was the entire families or it was the entire households, but one or two people used it a lot more. And so, we can still think of carbon and chlorine as sharing these two electrons. In other words, this is not an ionic bond. Carbon did not give up its electrons entirely to chlorine. They're still sharing. But because chlorine's a little bit stronger or more electronegative than carbon, it gets a little bit more of the electrons. So when we talked about ionic bonding, whenever one atom transferred an electron over to another atom entirely, they became cations and anions. Well, here, we're not sharing the electrons evenly, but we're also not transferring them entirely. And so what we expect is that the atoms exhibit what's called a partial charge. In other words, chlorine doesn't get both electrons entirely and become an anion, but it also doesn't take only half of each electron and stay neutral. So we think of chlorine, because it's more electronegative, as having some kind of partial negative charge, whereas carbon is going to have some kind of partial positive charge. And there are two different ways of showing this. One of them is to use what we call a delta symbol. And I'll come off to the side and draw that a little bit larger. It's a delta. It's a lowercase Greek letter. Just think of it as a number 8 that never quite closes up. And it just carries the meaning partial. So since chlorine's more electronegative and therefore holds the electrons a little more tightly than carbon does, we say chlorine gets a partial negative charge, which is just to say that it's not a zero charge, or chlorine is not neutral, but it's also not quite a -1 charge either. And if chlorine gets a partial negative, then we can say that carbon gets a partial positive. Now, perhaps a better way of imaging this is by using what we call the plus arrow. So it demonstrates the same thing that the partial charges do, but we put a plus sign over the positive element and point an arrow at the negative element. And at this point in the lecture, we could say they convey the exact same information, and in reality they do. But the plus arrow contains information that we like to call the bond dipole moment. In particular, because carbon is less electronegative than chlorine, and you end up with a negative pole and a positive pole, we call this a polar covalent bond. And earlier when we talked about chlorines, we call that a non-polar covalent bond. So they're both covalent bonds because the electrons are being shared. Whether they're nonpolar or polar indicates whether the electrons are being shared evenly or unevenly. And what's cool about this bond dipole moment is it'll help us a little bit later. In particular, where we start looking at not just individual bonds, but we start looking at the entire molecule and asking ourselves whether the entire molecule is polar or not. So just to look at this, bond just means that it refers to a specific bond and not necessarily an entire molecule. Dipole just implies that one of them has a negative charge and one of them has a positive charge. In other words, it is polar. And moment just means that there's a direction to it. In other words, we know as we go towards the chlorine, it becomes increasingly negative. So as an exercise, consider the three bonds I have down here. A carbon-fluorine bond, a silicon-oxygen bond, and a boron-chlorine bond. What I want you to do is draw the plus arrow, the bond dipole moment, for each of these polar bonds. I'm going to pause in the video for a few seconds to give you a chance to pause the video so you have plenty of time to make sure you're correct. So carbon is less electronegative than fluorine. So carbon gets the plus and the arrow points at fluorine. Silicon is less electronegative than oxygen, so it gets the plus and the arrow points at oxygen. And then same thing for boron and chlorine. Hopefully you had no trouble drawing those plus arrows. It's a pretty straightforward exercise. The real question is which one is more electronegative? That if you have two of the same element, then it's a nonpolar bond, and you have nothing to draw. That being said, before we move on, speaking of nonpolar bonds, something I would like you to commit to memory. Now, typically, whenever we deal with two atoms of the same element, it is always nonpolar. They always have the same electronegativity, and so it is always nonpolar anytime you're dealing with two atoms of the same element. Now, we're going to generally assume that it is always polar anytime you're dealing with two different elements. However, there are a few situations where you deal with two different elements, but we still consider the bond nonpolar. There is one that I want you to commit to memory, and you are absolutely expected to know that this bond is always nonpolar, and that is carbon and hydrogen. In particular, carbon and hydrogen being nonpolar is going to be a tremendous basis for our discussion in organic chemistry and biochemistry. So, carbon and hydrogen actually have almost identical electronegativities, and so they always share their electrons evenly, and these bonds are always thought of as nonpolar. So please commit that to memory, as it will pop up on your exam. Now, to finish off this particular lesson, I want to talk about something that's not covered well in your notes, and that is the net dipole moment. In particular, the net dipole moment is important when we stop looking at just a single bond and we start looking at a molecule made of many bonds. And it becomes very important to us whether the molecule is polar or not. So in particular, the net dipole moment is the sum of all bond dipole moments. Okay, so let's take a look at a couple of molecules. I'm going to start with carbon dioxide. Now, right now, you don't know how to draw the Lewis diagram of carbon dioxide. However, that is going to be one of the goals of our class, and in your next lesson, you're going to be learning how to draw Lewis diagrams, which is what this is. So what I want to do is I want to look at each one of the bonds for carbon dioxide, and I want to ask myself if is it polar or not. So I'll cover up our second oxygen, and so we're just looking at this carbon and this oxygen. Is that a polar bond? And if so, which one gets the plus, and which direction should the arrow be pointed? So hopefully you said that carbon was less electronegative, so it gets the plus. And the arrow points at oxygen. Now if we do the same thing for the other oxygen, again the carbon gets the plus, and the arrow points at oxygen. So now we've looked at each one of the two bond dipole moments. And something that we notice is that we have one arrow pointed directly to the right and one arrow pointed directly to the left. So I want you to think about something. If I'm standing on a specific spot and then I move 2 steps to the left, followed by moving 2 steps to the right, have I changed my initial position? No. But have I moved? Yes, I moved 4 steps. However, I have gone nowhere. In other words, what I'm trying to get across is the idea that the bonds can be polar, but the molecule can have no net dipole. In other words, here we have one bond that is polar to the right and one bond that is polar to the left. And since these two arrows are equal but opposite, we say they cancel each other out. And we would call carbon dioxide non-polar, because there is no net dipole. The two bond dipoles cancel out. So let's take a look at another molecule, in particular another one that's very important to you. Let's look at water. So my question to you becomes, is water polar? So let's look at each one of the individual bonds. Hydrogen is less electronegative than oxygen, so it gets a plus, and the arrow points at oxygen. Again, hydrogen gets the plus, and the arrow points at oxygen. So now we have a slightly different situation. Again, we have two arrows that do not necessarily add directly to each other, but they could not be said to be opposites either. So in other words, if we think of me as starting at one point, if I move 2 steps forward and 2 steps left, am I where I started? Absolutely not. In other words, you can't think of these two as canceling each other out. Okay? Therefore, there is a net dipole, and this molecule is polar. So now, just out of curiosity, thinking about how these two arrows should add together, could you draw the net dipole of this molecule? So The sum of two lines that are at right angle to each other is the line that bisects those two lines. So in other words, if they come to a right angle, the average is the sum. So plus here and a plus here. So the net dipole is a positive in between the two hydrogens, and the arrow still points at the oxygen. So we call it the net dipole. So let's do another exercise together before we end this particular lecture, just to make sure you've got a strong understanding of polar versus nonpolar. So I'm going to give you 5 molecules. We'll start with methane. We'll look at carbon tetrafluoride. So my question to you is, by looking at each one of the individual bonds and drawing their bond dipole moments, can you determine whether each one of these molecules is polar or nonpolar? So again, I'm going to pause for a few moments in the video to give you a chance to work on this on your own. I'll also take short pauses between each individual molecule as I solve it to see if you can do the remaining ones without moving forward. That way you can look at each individual one as an example before you look at the next one. So first, let's focus on CH4. Now, is the carbon-hydrogen bond a polar bond? Absolutely not. That's the one that we were just talking about that I wanted you to remember as always nonpolar. And so since each of the bonds in this molecule is nonpolar, we know that the molecule must be nonpolar. In other words, if there are no bond dipole moments, there cannot be a net dipole moment. Now let's take a look at carbon tetrafluoride. So this time we've got nothing but carbon-fluorine bonds. So we've already looked at this one. We know that carbon gets the plus and the arrow points at fluorine, and we could do the same for each one of the carbon-fluorine bonds. And now we've drawn all 4 of the bond dipoles. And that can help us think about whether this molecule is polar or not. So I have an arrow that's pointed right balanced by an arrow that's pointed left. I have an arrow that's pointed up, which is balanced by an arrow that's pointed down. In other words, every dipole moment has an opposite. And so each one of the dipole moments must be canceled out. So I would say there is no net dipole, and this is also a non-polar molecule. I'm going to pause for a few seconds to give you a chance to work on the following 3 with a little more time. So let's look at our third one. So this time we have one carbon-fluorine bond, and otherwise the other bonds are carbon-hydrogen bonds. So the carbon-fluorine bond has a plus arrow, indicating that bond is polar. Since the carbon-hydrogen bonds are each nonpolar, we have nothing to draw. So we have a single bond dipole moment, which has no other bond dipole moments to either add with or cancel out. Therefore, it is also our net dipole moment. And so since all of our arrows don't cancel out, we say this is a polar molecule. Let's take a look at our last two. We have carbon, fluorine, carbon, fluorine. So much like what we saw when we looked at H2O, we have two arrows that are at right angles to each other, which means they do not cancel each other out, and so there is a net dipole moment. So we would definitely call this molecule polar. And if you wanted to draw the net dipole moment, we know that if we have two moments at a right angle to each other, the net moment comes in between the two. So you still have a plus on the carbon, and the arrow comes in between the two fluorines to be the net dipole moment. And now we can take a look at this last one before we end this particular lesson. Plus arrow, plus arrow, plus arrow. So this time we have three arrows. We have one that's pointed to the right, but nothing that's pointed to the left. We have one that's pointed up, but nothing that one that's pointed up, and one that's pointed down. And our down are going to balance each other out and cancel out. In return, we have a single plus arrow left over. That, therefore, is our net dipole moment, and this molecule is indeed polar. If you have any questions about this lecture, it's not necessarily easy material, especially when we get to this last little bit looking at the molecules. And so if you have any questions, please contact me. Please come see me in my office. Please make some effort to come and talk to me. As these topics get more and more chemistry dense, they become harder and harder to understand on your own. So the plus arrows are really, really helpful, but hopefully you can also step back and start taking a look at the patterns of everything going on here. In particular, if we look at our first two molecules that were both nonpolar, what we can say about them is they were at the same in every direction. In other words, we have a carbon completely surrounded by hydrogens and a carbon completely surrounded by fluorines. So I would say this molecule is symmetric about its center. In other words, in regard to the carbon, it's the same in all directions. So even without drawing the plus arrows, because it's the same in all directions, I could very easily state that it is nonpolar. Same thing for carbon and hydrogen here. Because it is the same in all directions, I can definitely consider it nonpolar. However, if we take a look at our very first molecule here, on three sides of the carbon we have hydrogen, which is not very electronegative and is nonpolar with carbon. On another side we have fluorine, which is the most electronegative element. So because it's not balanced, fluorine is only on one side but not on the other. In other words, it's not symmetrical about its center. We know it's polar. Same thing could be said for our second and third molecules. One side of the carbon has the fluorines, one side of the carbon has hydrogens. So we know this is a polar molecule because it's different on one side than it is on the other. This one's a little less even, but either way, you've got fluorines that are balanced in the up and down, but we still have most of our fluorines to one side of the carbon, and then the other side has a hydrogen, which is nonpolar. And so even at a glance, it's relatively easy to determine whether these are polar or nonpolar once we have the periodic trends of electronegativity down in our heads. So hopefully that gave you some clarification on the notes and the lecture, and see you next time.